light behaves like a particle and a wave. And an example of the wave behavior of light is interference, reflection, refraction, and so on. And an example of the particle behavior is the photoelectric effect. Now, light is essentially an electromagnetic wave that can propagate through a vacuum. So the speed of light through a vacuum is around 3 by 10 to the 8 meters per second. And other waves, like a ripple through water for example, need a medium to propagate. And a sound wave is another example of a wave that requires a medium to propagate. So essentially a wave is a disturbance that transfers energy without transferring matter between 2 points. Now light waves are transverse, so they comprise electric and magnetic fields, and these vary with time, and they oscillate perpendicular to the direction of propagation of the wave. Now consider this light source. So the waves that propagate away from the light source are spherical in 3 dimensions. But if we consider this plane, we can see that the circles represent the position of the wavefront away from the light source. And a wavefront comprises photons that oscillate in the same phase and at the same frequency. So you can imagine these photons oscillating back and forth out of the screen. So on this wavefront moving outwards, the photons are fully out of the screen. And if we trace out the wavefront based on the oscillations of the photons in and out of the screen, it looks something like this. And this point where the photons are out of the screen is called the crest. And between these positions of the wavefront, we have the trough. And we draw light rays emanating from the light source. And these rays are perpendicular to the wavefront at each of those points. So they're pointing in the direction that the light wave is traveling, in each of those directions. So another example here is this ripple in a pond. So we can observe the movement of the wavefront, where the particles of water are in a maximum upward direction, and in between, the water particles are in a downward direction. So you see like a sinusoidal oscillation as you move away from where the rock was dropped. And we'll look at waves in more detail in the next unit, but for now, we're going to use light rays to determine the behavior of light, which is essentially geometric optics, where we neglect the wave nature of light. So these rays interact with surfaces, and parts of these rays get refracted or bent as they travel through a surface, and some of it gets reflected from the surface. So note that rays are not sufficient to understand the spread of light, so the wave nature of light needs to be studied, where we have interference between waves and diffraction, which we'll look at later on. Now visible light, or the light that we can see, makes up a small part of the electromagnetic spectrum. So this comprises radio waves, which have the lowest frequency, up to gamma rays with the highest frequency. So as we can see, frequency increases as we go up the spectrum. So for example, you may have a light wave that oscillates like this, whereas at the lower frequency it may oscillate like this. So radio waves have a lower energy than gamma rays. So you have a larger wavelength compared to the upper part of the spectrum. And we're going to use ray diagrams to predict the path of light before and after it interacts with matter. Light that is incident on a surface can be reflected. And the law of reflection states that the angle of incidence, being the angle between the incident ray and the normal to the surface, which is this angle over here, is equal to the angle of reflection. So that's the angle between its reflected ray and the normal to the surface at this point. And this can be proven using the Huygens-Fresnel principle, which states that every point on the wavefront is a source of spherical wavelets. And these secondary wavelets that emanate from these points mutually interfere with each other. So as they propagate, they end up being spherical themselves. So using this principle, we consider this light ray and the propagation of this wavefront to the surface. So when this wavefront hits the surface, it looks something like this. So when we're looking at a small part of the surface, compared to the distance from the light source, the further away the spherical wave is from the light source, the spherical wave appears more and more like a plane wave. And that's how we'll treat the wavefront. So as we said, the wavefront is perpendicular to the light ray, and at some point on the wavefront, we have a secondary wave emanating from this point, according to Huygens' principle, and the distance that this wavefront travels from this point is the speed of light multiplied by time t. And note that the speed of light is approximately equal to c in air also. Now after this incident wave w collides with the surface, it gets reflected. And the reflected wavefront is seen by this hemisphere above the surface. So the blue reflected ray is perpendicular to this wavefront. And this blue line here represents the reflected wavefront, which is tangent to this circle at this point. So by geometry, we can see that this angle is equal to the incident angle. So the angle that the ray makes with the normal to the surface is equal to the angle between the wavefront and the surface. And on this side, we denote the angle between the reflected wavefront and the surface as theta r. Now the time taken for this secondary wave to collide with this surface is the same as the time taken for the reflected primary wave to travel the same distance from this surface. So therefore, if the length of this reflected ray is ct, then these two edges are identical. And these two angles are also identical. So therefore we have two right angle triangles that have a common edge at this surface, and they have a common angle, and the other edge has the same length. So these two triangles are congruent. And that means that theta I is equal to theta r. And I'll leave it for you to show that theta r is the same as the angle between a reflected ray and the normal to the surface. And you can visualize that using basic geometry. Specular reflection is the reflection of light from a relatively smooth surface. So in this case, the normal to the surface is relatively constant. So therefore the angle of incidence, or the angle that the incident light ray makes with the normal, is equal to the angle of reflection, or the angle between a reflected light ray and the normal to the surface. Now on the other hand, diffuse reflection is the reflection of light from a rough surface. And this results in light being reflected in many different directions because the normal to the surface varies along its area. So for example, at this point, the normal to the surface may be in this direction, and therefore the angle of incidence being equal to the angle of reflection results in a reflected ray that points in this direction. Whereas at this point, the normal to the surface is in this direction, so the incident angle in this case is 0, and therefore the angle of reflection is 0. So the reflected ray points in that direction. And over here, the normal to the surface points upwards, so the angle of incidence being equal to the angle of reflection results in a light ray that gets reflected in this direction. A mirror is an optical device that forms an image by reflecting light. And four things we're looking for are the position of the image, whether the image is real or virtual, and also whether the image appears upright or inverted, and whether the image is magnified or enlarged or diminished, which means it appears smaller. And the first type of mirror that we'll look at is a plane mirror. So the mirror is essentially flat, and we see the normal to the surface at this position, and it's constant along the height of the mirror. And we refer to the principal axis as the axis that's perpendicular to the mirror at the vertex of the mirror, which we take as the midpoint. Now if we consider this to be an object, and incident light rays emanate from this object and hit the mirror, then by the law of reflection, the incident angle to the normal is equal to the reflected angle. So the reflected ray looks like this. And if we look at this other incident ray, then it gets reflected in a similar manner. So these two reflected rays are parallel. And note that when we look at a flat mirror, we see the image inside the mirror. So if you extend the line from these reflected rays, we can construct the image. So here we have DO as the distance from the mirror to the object, and DI as the distance of the mirror to the image. So the distance from the mirror to the image is the same as the distance from the mirror to the object. And here the image is virtual because we perceive it as appearing behind the mirror. So it's not a real image. So essentially, if we see these rays that are reflected from the mirror, we perceive the image being behind the mirror. And in the case of a plane mirror, the image is upright, and also the image is the same size, so it's not magnified or diminished. And note that these rays never meet, so they don't focus at the object or the image. So the focal point for a plane mirror is at an infinite distance from the mirror. Now if we look at a spherical mirror, so basically it's a mirror that forms a part of a sphere. So here we have the vertex of the mirror, which is in the middle, and the principal axis being perpendicular to the mirror at the vertex. Now if a light ray that's parallel to the principal axis is incident on the mirror, then according to the law of reflection, the reflected ray is going to have the same angle from the normal to the mirror at this point. So as we can see, the normal varies along the mirror. So essentially the reflected rays pass through the focus. And in a similar way, if we have an incident ray that's parallel to the principal axis coming from the bottom, then the reflected ray is going to be in a direction such that it forms the same angle with the normal as the incident ray at this point, by the law of reflection. And similarly, if we had an incident ray from the center of curvature along the principal axis, then a reflected ray goes back along the same direction by the law of reflection. So therefore all these reflected rays pass through the focus. So this is true for small spherical mirrors, or where the light rays are close to the principal axis. And considering r to be the radius of curvature of the sphere, which is essentially the distance from the center to the vertex, then the distance of the focus from the vertex is around 1/2 of the radius of curvature of the sphere. So essentially, if we have a very large spherical mirror, the radius of curvature gets larger and larger, and the focus goes to infinity. So we essentially approach a plane mirror. Now for a parabolic concave mirror, which is the main concave mirror that we look at, so again we have the vertex and the principal axis, being the axis perpendicular to the mirror at the vertex, and we have an incident light ray which gets reflected at the same angle from the normal to the mirror at this point. And again, if we have another parallel light ray to the principal axis, that gets reflected in a similar manner. So all the reflected light rays pass through the focus. And here we measure the distance of the focus from the vertex and denote it as f. So for a parabolic concave mirror, the reflected light rays, due to incident light rays that are parallel to the principal axis, converge at the focus. So suppose we have an object at this position, and we want to determine what the image looks like. Well, we send an incident ray parallel to the principal axis, and we know this will get reflected through the focus. And we send an incident ray through the focus, and that gets reflected in a direction that's parallel to the principal axis. And the intersection of these rays shows us where the image is formed. And we'll derive a formula to be able to calculate the position of the image. And in this case, because the image is in front of the mirror, it's real. So essentially you can put your hand there, or a screen, and you'll be able to see the image at this position. And we see the image is upside down, so it's inverted. And the image is smaller, so it's diminished. And similarly for a convex parabolic mirror, we have the principal axes being perpendicular to the mirror at the vertex. So if we have an incident light ray, by the law of reflection, the reflected ray looks something like this. And we have another incident light ray parallel to the principal axes, so that'll get reflected in this manner. And if we extend these reflected rays, they meet at the focus. So this time for a convex mirror, the focus is behind the mirror. And as we saw for the concave mirror, the focus was in front of the mirror. Let's derive the mirror equation using a concave mirror, and we'll use a sign convention to be able to apply it to convex mirrors. So consider a concave mirror with a focus at a distance f from the vertex, and we have the principal axes being normal to the mirror, and we consider this object at some distance SO measured from the vertex of the mirror. So if an incident light ray goes through the focus, then a reflected ray will be parallel to the principal axis. And if we consider another ray hitting the mirror at the vertex, then by the law of reflection, the reflected ray will be reflected at the same angle. So we expect the image to be somewhere here. And we denote the distance of the image from the vertex as SI. So if we consider this triangle and this triangle here, the angle of this triangle is equal to this one, and they're both right triangles with an angle of 90 degrees, and we'll take the height of the image as HI and the height of the object as H subscript O. So the ratio of the heights of those triangles is equal to the ratio of their lengths, because they're similar triangles. And now we'll consider this triangle and this triangle here. So these triangles have the same angle, and they're both right triangles. So the length of this triangle's base is SO, which is the distance from the vertex to the object, minus the distance from the vertex to the focus, and that's divided by the length of this triangle, which is the distance from the vertex to the focus, being F. And that's equal to the ratio of the heights of those triangles. So that will be the height of the object on the height of the image. And note that this is an approximation, because as we can see, the focus is measured from the vertex, and this right triangle ends here. But it's still a good approximation for a parabolic mirror. So therefore, if we equate these two equations, we get another relationship. S0 on SI is S0 on F minus 1. So if we divide through by SO, and add the reciprocal of SO to both sides, we get another relationship, being the reciprocal of the distance to the object plus the reciprocal of the distance to the image is equal to the reciprocal of the distance to the focus. And if we take the reciprocal of both sides of this equation, we get the height of the image on the height of the object is the distance to the image on the distance to the object. So if we take the absolute value, we get the magnification. But if we want to account for the image being inverted, we can take M as HI on HO and put a negative sign behind SI. Now let's look at these equations in a bit more detail. So firstly, if the mirror is concave, then the distance to the focus is taken as positive. So it's in front of the mirror. But for a convex mirror, so it looks something like this, where the object is on this side, the focus will be on the opposite side as the object. So the distance to the focus here is negative. Now if the distance to the image is positive, so the image is on the same side of the mirror as the object, then the image is real. But if we end up getting a distance to the image being negative, so for example where we have a convex mirror, then the image is virtual, so it's on the opposite side of the mirror compared to the object. Now if we consider the magnification, and given the height of the object is positive, then if the height of the image is positive, then M is also positive, and therefore the image would be upright. And on the other hand, if the height of the image ends up being negative, then M would be negative and the image would be upside down or inverted. So note that for consistency, we'll put a negative sign behind the distance to the image, because if the image ends up on the same side as the object, meaning SI is positive, then as we can see, the image is flipped upside down. And where the image ends up on the opposite side of the mirror compared to the object, we'd have negative negative SI, so the image would be upright in that case. And we'll get some more practice in applying these mirror equations. We've seen that ray diagrams can tell us the location of an image, the type being real or virtual, and the orientation being upright or inverted when an image is formed by a mirror. So generally, to find images formed by mirrors, we use three principal rays, and these are the incident rays that are parallel to the principal axes. And the other principal ray is the ray that reflects where the principal axis intersects the mirror. So we know the angle of incidence is equal to the angle of reflection. So the incident ray will be reflected as follows. Given these angles to the normal of the mirror at this point are equal. by the law of reflection. And the other principal ray is the one that passes through the focus of the mirror. So the reflected ray is parallel to the principal axis. So here in the case of the convex mirror, we have a principal ray being parallel to the principal axis. So the reflected ray ends up going in this direction. And if you extend this reflected ray, it goes through the focus, which is behind the mirror. And the other principal ray looks like this for a convex mirror. So we have the angle of incidence being equal to the angle of reflection. And in this case, we can't really have a light ray going directly through the focus, as the focus is behind the mirror. So in general, we'd use these two types of principal rays for the case of a convex mirror, for example. Consider a convex mirror with a focal length of minus 40 centimeters. So the focus is behind the mirror. Now if an object with a height of 5 centimeters is placed at 20 centimeters in front of the mirror, in part A, we're asked to find where the image is located. So recall the mirror equation being the reciprocal of the distance to the object plus the reciprocal of the distance to the image is the reciprocal of the focal length. So S0 is 20 centimeters plus 1 over SI is equal to 1 over the focal length. So given the focus is behind the mirror, we have minus 40 centimeters. So therefore, subtracting 1 on 20 from both sides, we get 1 on SI is minus 0.075. And solving for SI, we get minus 13.3 centimeters. So the image is located somewhere here, being behind the mirror. Now is it a real or virtual image? Well, given the image is behind the mirror, then it's a virtual image. Now is the image upright or inverted? Well, remember the magnification equation was equal to the height of the image on the height of the object, which was equal to the negative of the distance to the image on a distance to the object. So therefore this ratio is minus SI, and SI was negative 13.3 centimeters divided by SO, which is 20 centimeters. So therefore M is 0.67. So given that this value is positive, then the image is upright. And now to find the height of the image, we just multiply this ratio, which gave 0.67, by the height of the object. So what we get is HI is 0.67 by the height of the object, being 5 centimeters, which gives 3.3 centimeters. We saw that an incident beam of light on a surface, which makes some angle with the normal to the surface at this point, being the incident angle, gets reflected by the same angle. So it makes the same angle with the normal to the surface. So while part of this beam of light gets reflected, part of it gets transmitted through the surface. And as it gets transmitted from one medium to another, it gets bent or refracted. So refraction is a change in the direction of a light ray as it passes from one medium to another. And it results due to the speed of light changing as it enters a new medium. Because light gets absorbed and emitted by the atoms of the medium, so it'll travel slower compared to its speed in a vacuum. Now the index of refraction of a medium is inversely proportional to the speed of light in that medium. So the constant of proportionality is the speed of light in a vacuum. So the index of refraction is the speed of light in a vacuum on the speed of light in a given medium. So if we turn this equation around, we get the speed of light in a given medium is the speed of light in a vacuum on the refractive index of the medium. So for clarity, the refractive index of water is around 1.33 and the refractive index for air is close to 1.0. So light travels faster in air than it does in water. So when light gets bent or refracted as it enters a medium, we still measure the angle of refraction relative to the normal of the surface. So let's call this medium 1 and this medium 2. So therefore we'll take the angle of incidence in medium 1 as theta 1 and the angle of reflection in medium 1 as theta 1 dash. And therefore the angle of refraction in medium 2 will take as theta 2. So again, using the Huygens-Fresnel principle, where each point on a beam of light is a source of secondary wavelets that interfere with each other. For this incident beam, part of it gets reflected, so this will be our reflected wavefront, and part of it gets transmitted and bent or refracted. So this here will be our refracted wavefront. So by geometry, this angle theta 1 is equal to this angle theta 1 that the incident wavefront makes with the surface. And given that this angle between a refracted ray and the refracted wavefront is 90 degrees, and this here is our angle of refraction, then given this angle is 90 degrees, this angle here of this triangle will be 90 degrees minus theta 2. And then if you subtract these two angles from 180 degrees, you'll get this third angle of this triangle being equal to the angle of refraction. So the distance that this secondary wavelet travels in medium 1 to the surface at time t is the speed of light in medium 1 by time t. And at the same time, this secondary wavelet is getting refracted through the medium. So over the same time, it'll travel a distance of the speed of light in the second medium multiplied by time t. So that will be this distance over here. And now using trigonometry, we see that sine theta 1 is equal to the opposite edge on the hypotenuse. So let's just call this distance h. And sine of the angle of refraction is equal to the opposite edge on the hypotenuse. And now if we divide these together, we get sine of the incident angle in medium 1 on the sine of the refracted angle in medium 2 is V1 on V2. And now using this relationship, the speed of light in medium 1 is the speed of light in a vacuum on the refractive index of medium 1, and similarly V2 is C on N2. So the C's cancel and N2 ends up in a numerator. So finally multiplying through by N1 and sine theta 2, we get N1 by sine theta 1 equals N2 by sine theta 2. And this is called Snell's law, which relates the angles of incidence and refraction of a light ray that's passing from one medium into another to the indices of refraction of medium 1 and medium 2. So when light travels from a medium with a lower index of refraction to a medium with a higher index of refraction, or a denser medium, the light ray gets bent or refracted towards the normal. So therefore the incident angle will be greater than a refracted angle. But if the light beam travels in the opposite direction, so if we take the bottom medium as 1 and the top medium as 2, so in this case the index of refraction of medium 1 will be greater than that of 2, then we see the beam of light getting refracted away from the normal. So in this case the incident angle will be lower than a refracted angle. And if the incident light ray travels along the normal to the surface, then the angle of refraction will be 0. So it'll just travel straight down. So to best remember these relationships, you can see that if N1 is lower than N2, for example, then theta 1 must be higher on this side for this equation to balance. Recall that we had an incident beam of light traveling from a medium 1 to medium 2. We had theta 1 as the incident angle and theta 1 dash as the angle of reflection. So part of this ray gets reflected and part of it gets refracted in medium 2. So by Snell's law, we had the index of refraction of medium 1 by sine of the incident angle in medium 1 is equal to the index of refraction of medium 2 by sine of the angle of refraction in medium 2. Now suppose N1 is greater than N2. So remember, for this case, the incident angle must be less than the angle of refraction for this equation to balance. So therefore in this case, the incident angle is less than the angle of refraction, meaning that the incident light beam gets refracted or bent away from the normal to the surface. Now if we keep increasing the incident angle, the refracted beam keeps going away from the normal, as we can see, until we reach this critical case, where the incident angle becomes a critical angle. So at the critical angle, the light ray refracts at 90 degrees to the normal, to the surface, so it travels along the surface of the material. And at this critical angle of incidence, we take theta 2, being the angle of refraction, as 90 degrees to the normal to the surface. So therefore sine theta 2 evaluates to 1, and then dividing through by n1, we get n2 on n1, and taking the arcsine of both sides, at the critical angle, we get theta c is equal to the arcsine of n2 on n1. So this is called total internal reflection, where for light rays with an angle of incidence beyond the critical angle, all the light gets reflected. So no light gets transmitted to the other medium. And note that this is only true where the index of refraction of medium 1 is greater than that of medium 2. So this can be seen if you take the sine of both sides. So we have n2 on n1. So therefore n1 must be greater than n2. Because remember that the range of sine theta is from -1 to 1. A diver shines a torch from the bottom of a lake that has a depth of 15 meters. And a light beam emerges at a small incident angle from the vertical. So the torch would be at the bottom of the lake and be oriented at some angle from the vertical. And in part A, we're asked for the depth that the torch would appear to a person in a boat. We'll recall Snell's law, which states that the refractive index of medium 1 by the sine of the incident angle is equal to the refractive index of medium 2 by the sine of the angle of refraction. So we know that water is denser than air, so the angle of incidence will be lower than the angle of refraction. So the light ray will refract away from the normal to the surface. So we'll denote the normal by this dashed line. So by geometry, these two angles are equal. And let's denote this distance here as x. So if we extend this refracted ray, the torch is going to appear to a person in a boat as if it's shining the light from this position here. So we'll take this position as the y position of the torch that we're looking for. Now by geometry, tan of theta 1 is equal to the opposite edge of that triangle on the adjacent edge, which is the depth of the lake at 15 meters. So given this is the refracted angle, by geometry this angle is equal to this one. So therefore tan theta 2 is equal to x, which is the length of this edge of our right triangle, over the adjacent edge. So if we divide these two expressions, we get tan theta 1 on tan theta 2 is equal to y on 15. And note that we're told that the light beam from the torch emerges at a small incident angle. So given tan of an angle theta is sine theta on cosine theta, for small angles much less than 1, cosine of theta is approximately 1, and therefore tan theta is approximately equal to sine theta. So we can replace these two expressions as sine theta 1 on sine theta 2. So given the refractive index of water is approximately 1.33 and the refractive index of air is around 1.0, then by Snell's law, sine theta 1 on sine theta 2 is equal to n2 on n1. And solving for y, the torch is going to appear at a depth of around 11.3 meters. Now how far can the boat be to see the light emitted from the torch? Well, recall that total internal reflection occurs at some critical incident angle from the normal. So at this angle, all the light will be refracted along the surface. So therefore the refracted angle to the normal will be 90 degrees, and therefore the critical angle will be the arc sine of n2 on n1. So as we can see, the refractive index of the incident medium is larger than that of our second medium. So if you substitute for the refractive indices of both mediums, we get a critical angle of 48.753 degrees. And therefore this horizontal distance can be calculated using trigonometry. So we'd have tan theta c is equal to the opposite edge on the adjacent edge, being the depth of the lake, and solving for x gives you a distance of around 17 meters. A thin lens is an optical device that forms an image by refracting light. So conversely, a mirror forms an image by reflecting light. And here we look at thin lenses, meaning the refraction of light through the material is ignored. So for example, if you consider this prism, we have an incident light ray from air to glass. So recalling Snell's law, we have n1 sine theta 1 is n2 sine theta 2. So if light goes from a medium with a lower index of refraction, then the incident angle is higher than a refracted angle. So at this point, the incident angle with the normal is as follows, and the refracted light ray refracts towards the normal. And then on the other side, we have another incident angle with this normal, and because the light ray travels from a denser medium to another medium, then it gets refracted away from the normal. So therefore the refracted angle is higher than the incident angle. But with a thin lens, where this width here is much smaller than its height, then we ignore the refraction in the material, and therefore we draw our incident light rays as going up to the line that passes through the optical center. And specifically, this is a biconvex lens because it has two convex sides. Now for a thin convex lens, so this is called a converging lens, because incident light rays that are parallel to the principal axis, which is the axis that passes through the optical center, get refracted, and these transmitted light rays all converge to a common point on the transmitted side of the lens. So this is called the focal point. Now for thin concave lenses, so a concave lens is a diverging lens because incident light rays that are parallel to the principal axis get refracted and they diverge, as we can see. But if we extend these rays, they appear to have originated from a focal point on the incident side of the lens. So this here is called a virtual focus, because the light rays don't actually converge to it. Now a real image is formed by a lens when light rays originate from a common point. So for example, if we had an object and we take a light ray from this point along the principal axis, so that gets refracted through the focus, and a light ray through the optical center does not get refracted. So the image gets formed on the transmitted side of the lens. So in other words, for a real image, the light rays from a common point are refracted and intersect at another common point. And note that light rays going through the optical center do not get refracted. Now suppose we had another object here and we took an incident ray along the principal axis going towards the concave lens. That's going to get refracted as follows. And then if we extend this ray through the focus, it looks something like this. And if we take another ray and pass it through the optical center, it doesn't get refracted, and therefore the image is formed on the incident side. So this is called a virtual image because these refracted light rays diverge away from each other, but the intersection is here, so they appear to have originated from this point, and therefore the virtual image is formed on the incident side of the lens. The thin lens equation is derived in a similar way to the mirror equation. So we have an incident ray going along the principal axis, which gets refracted through the focus, and another incident ray going through the optical center, which doesn't get refracted. So using the intersection point, we can determine where the image is formed. So this is a real image because it gets formed on a transmitted side, where the light rays are refracted. So if we take HO as the height of the object, and HI as the height of the image, and the distance from the optical center to the object as SO, and from the optical center to the image as SI. So because these two angles are equal, then the triangles are similar. So the ratio of the height of the image to the height of the object is equal to the ratio of the distance to the image on the distance to the object. Now similarly, these two angles are equal, and therefore these two triangles are also similar. So therefore the ratio of the height of the image to the height of the object, where the height of the object is the height of this triangle, is equal to the ratio of this edge, which is SI, minus the distance of the optical center to the focus, over this distance from the optical center to the focus. So therefore, if we equate these two equations, we have SI on SO is equal to SI on F minus 1. And then if we divide through by SI and solve for the reciprocal of the focus, we get the reciprocal of the distance to the image plus the reciprocal of the distance to the object is equal to the reciprocal of the focal length. And the magnification of the image is the ratio of the height of the image to the height of the object. Now we take the distance to the object as always positive because it's a real object, and therefore we take the distance to the image as positive if the image is on a transmitted side, where the light rays get refracted to a common point. So SI is greater than 0 for a real image, and therefore SI is less than 0 for a virtual image, which would appear on the incident side. Now for a convex lens or converging lens, where incident light rays from a common point get refracted and converge to a common point, we take the focal length to be positive, where the focus is on a transmitted side of the lens. And therefore for a concave or diverging lens, the focal length is negative. So the focus in that case will be on the incident side of the lens. Now given that the height of the object is always positive, then we put a negative sign behind the distance to the image. So the reason for this is because real images have SI greater than 0 and they appear inverted on a transmitted side of the convex lens. And given the distance to the object is always taken as positive, then to account for the image being inverted, we just negate the distance to the image. And if we take the absolute value of the magnification, that gives the ratio of the magnitude of the size of the image to the size of the object. And we'll get some practice in using these equations for a thin lens. As we saw briefly, we can use ray diagrams to determine the position of the image relative to the optical center, the type of the image being real or virtual, the size of the image being its height, and its orientation being upright or inverted. And generally, when we use ray diagrams, we use three principal rays. So suppose we had an object somewhere here. One of the principal rays we use to locate the image is the one that's parallel to the principal axis. So as we can see, this is refracted through the focus. And the other principal ray is one that passes through the optical center of the lens. So this principal ray does not get refracted. And if we look at both focal points of this biconvex lens, then the other principal ray is one that passes through the focus. So this gets refracted along the principal axis. And we can locate the image where these rays intersect. So this here is the third principal ray. And don't get confused between this focus and this one, because the real focus is taken on a transmitted side of the lens when we apply the thin lens equation. And you can also use these principal rays for a concave lens. So if we had an image like this, then this principal ray is going to get refracted, so it diverges. But if we extend it, it passes through the virtual focus. And the incident ray through the optical center doesn't get refracted. So the intersection of these two rays emanating from this point tells us where the image is. An object with a height of 10 centimeters is placed 35 centimeters in front of a diverging lens, which has a focal length of 15 centimeters. So that's measured from the optical center. So the object would be somewhere around here. And we'll label the distance from the optical center to the object and the height of the object. Now in part A, we're asked where the image is located. So using the thin lens equation, we have 1 over the distance to the object plus 1 over the distance to the image is equal to the reciprocal of the focal length. So SO is 35 centimeters plus the reciprocal of SI is equal to 1 over the focal length. So in this case, because we have a diverging lens, we negate the focal length. So if we solve this equation, we get the distance to the image as minus 10.5 centimeters. So it's going to be located somewhere here, on the incident side of the lens, being negative. Now is the image real or virtual? Well, because it appears on the incident side of the lens, then it's a virtual image. And now let's determine if the image is upright or inverted. So to do that, we use the magnification equation, which is a ratio of the height of the image to the height of the object, being equal to minus the distance to the image on the distance to the object. So because SI is negative, then this ratio is positive, and therefore the image is upright. And now let's find the height of the image. So if we solve this equation for HI, we have HI is the height of the object by the negative of the distance to the image on the distance to the object. So given the height of the object is 10 centimeters, And the distance to the image we determined from part A as minus 10.5 centimeters. And the distance to the object is given in the problem. Then we can determine the height of the image, which is 3 centimeters. So therefore, the image looks something like this. So we can see it's about right if we do some ray tracing. So we have a principal ray along the principal axis, which gets refracted something like this. So if we extend the refracted ray to the focus, and then we pass another ray through the optical center, which doesn't get refracted. So because this drawing is not to scale, the location and height of the image are slightly off from the calculation. So our result, using the lens equation, looks correct. A wave is a continuous disturbance that transfers energy between two locations without transferring matter. So if we look at this simulation of a wave propagating through a string, and I'll link this below in the description so you can experiment with it yourself. So we'll pick the oscillate option, effectively moving one end of the string up and down continuously. And that sends a disturbance in the string. So effectively, if we track one of these particles, so this green particle for example, it moves up and down in the same spot. So there's no particles traveling through the string. Now a wave pulse, on the other hand, is a single disturbance that transfers energy between two locations of the string. So if we move the end of this string up and down once, then we can see the pulse propagating through the string. So a wave is continuous, whereas a pulse is not. And because a wave is periodic, so we can see that it repeats, we can model it as a continuous periodic disturbance with a well-defined wavelength and frequency. So let's have a look at these properties. So if we look at a particle in the string at some position, and if we plot its displacement from the equilibrium position versus time, we see the particle starts at equilibrium, then moves upwards by a certain amount, goes back through equilibrium, and then moves downwards by the same amount, and goes back towards equilibrium. So this marks one cycle. And the time it takes to complete this cycle is called the period of the oscillation. And we can take the period from peak to peak. So for example, where the particle starts from this position and ends up back at this position is the same time that it takes to complete one cycle. Now the frequency of the oscillation is the number of cycles that the particle completes in 1 second. So that has a unit of hertz. And we've seen in the harmonic oscillator that the period is related to the frequency, being the reciprocal of the frequency. Now the wavelength, on the other hand, is obtained if we plot the displacement of the particles in the string versus the position along the string. at a particular time. So for example, this here is our string, and as the disturbance moves through the string at some velocity, the particles are going to oscillate in this manner. And in this case, the distance between two particles that are displaced by the same amount is called the wavelength. So that can be the distance between the peaks or the crests. Distance between the troughs is also the wavelength. Or this distance over here is also the wavelength. So basically it's the length of the wave, which is periodic, so it repeats along the string. Now another example of a wave is a sound wave. So for example, if these strings of the guitar are plucked back and forth, they're going to disturb the air particles around them. Then you get a wave propagating through air. So a particle that was here, for example, being the equilibrium position, oscillates between 2 points, and in turn disturbs the air particles around it. So this creates regions of high pressure in the air. So these are the compression regions. And we'll look further into the variations of pressure in a medium due to a sound wave when we'll look at sound waves in more detail. So these two examples of a wave through a string and a sound wave are examples of mechanical waves. Or in the case where we're looking at a single pulse, that's called a mechanical wave pulse. So mechanical waves or wave pulses require a medium to propagate. So here sound moves through air, and a wave moves through a string. But electromagnetic waves, on the other hand, or light waves, do not require a medium to propagate. So remember that light behaves like a particle and a wave, so it can create its own disturbances. So for example, light going from this flashlight has a wavefront that moves in this direction, and the photons oscillate back and forth in the direction perpendicular to the motion of the wavefront, which creates perpendicular electric and magnetic fields. So the electromagnetic wave looks something like this. And we'll also look at electromagnetic waves in more detail. Recall the wave propagating through a string which has some length L, and generally the speed at which the wave or wave pulse propagates through a medium depends on the type of wave and the properties of the medium. So for an electromagnetic wave, the speed of all electromagnetic waves in a vacuum, which is a universal physical constant, is equal to around 3 by 10 to the 8 meters per second, being the speed of light in a vacuum. Now consider our string here and the speed of the wave going through the string. And if we cut out a small part of this string and blow it up here, the length of this section of string is delta L. And we're not doing calculus here, so we'll just assume this is a very small length. So before sending a disturbance through this string, suppose a tension force was applied to the string. And while this tension force was in a string, the string was plucked up and down continuously at one end, and this wave propagated through the string. So therefore, we have the tension force throughout this string being uniform, and then we take the center of curvature of this length of string as C, and the radius of curvature being the distance from C So the line of the radius of curvature is perpendicular to the arc of the string at this point, and same on this side. And this angle here we take as delta theta, which is equal to this angle. So by geometry, this angle will be delta theta, and so will this angle. And the same on this side. Now if we suppose we're moving along with the wave, so for example, we're standing on this wave, and moving along with it, so therefore this element of the string is going to appear to be moving to the left at the same speed as the wave. Now if we take a sum of forces in the horizontal direction, we have minus ft cosine delta theta plus ft cosine delta theta. So given the forces balance, then the string element is in dynamic equilibrium in the horizontal direction. And if we take a sum of forces in the vertical direction, so note that this force, being tangent to the string at this point, is resolved into horizontal and vertical components, and same with the force on this side. So in the vertical direction, this component has a magnitude of ft sine delta theta. And we have two components of force acting downwards, so we multiply by 2. And we're going to use a small angle approximation, meaning that sine of the angle is approximately equal to that angle for angles much less than 1. So therefore we take sine delta theta as delta theta. And therefore the net force is assumed to act towards the center of curvature for small angles. So as this element of the string moves at some speed, the net force acting on it towards the center of curvature is equal to the mass of this element of string, which we'll take as delta m, by the speed that this element of string is moving relative to our observer that's moving along with the wave at a constant speed. So that's equal to the wave speed squared on the radius of curvature. So note that given our small angle approximation, we assume that the vertical component of force points towards the center of curvature and gives rise to a centripetal acceleration. Now if we multiply through by rho, we have rho by 2 delta theta by the tension force in the string is equal to delta m by the wave speed squared. And by geometry, we can see that rho by 2 delta theta is equal to delta L, which is the arc length of the element of string. So we can replace this with delta L, and solving for the wave speed through the string, we have Vs is the square root of the tension force by delta L on delta M. Or alternatively, we can write this as a square root of the tension force on delta M on delta L. And this is the linear mass density, or mass per unit length of the string, which is typically denoted as mu being the mass per unit length. So this ratio is equal to m on L, where the mass density is uniform in a string. So we can finally write this expression as m on L. So therefore a higher tension force in a string results in a higher wave speed through the string. And let's have a look at this using our simulation. So if we send a pulse through this string and set the tension in the string to be very low, we can see it's propagating slowly. And if we increase the tension in a string, it gets faster and faster, as expected. In a given medium, the speed of sound increases with the temperature of the medium. So the speed of sound in a gas medium, like air, can be derived using the wave equation, and it's equal to the square root of the adiabatic constant by the universal gas constant by the temperature of the medium over the molecular mass of the medium. So the adiabatic index for air is 1.4, and the universal gas constant is 8.314 joules per mole Kelvin, which you've seen in the thermodynamics part of the course. And the absolute temperature in Kelvin of a medium that has a temperature of 20 degrees Celsius is 293 Kelvin. And the molecular mass of air is around 28.96 grams per mole. So if you converted the molecular mass to kilograms per mole, you'll get the speed of sound in air being around 343 meters per second at a temperature of 20 degrees. Now in a solid, such as steel for example, the speed of sound can also be derived from the wave equation, and that's equal to the square root of the Young's modulus of steel, which is basically the stiffness of the material, on the density. So this generally applies to a solid subjected to a dynamic force along its axes, which causes a disturbance in the material. So the speed of sound through steel is around 5900 meters per second. And for a liquid such as water, the speed of sound is equal to the square root of the bulk modulus on the density. So in water, the speed of sound is around 1480 meters per second. So recall our string example. The higher the tension force in the string, meaning the string is stiffer and doesn't move as much in the vertical direction, the higher the wave speed through the material. And this is similar in concept to the speed of sound, except sound waves can be visualized as pressure waves. So as a sound wave propagates through a medium, and noting that we're looking at this medium at a particular point in time, the particles get bunched up in the compression regions when the sound wave propagates through the medium, and these are the regions where the pressure is the highest. And then in these empty regions, which are called the rarefaction regions, you get a negative pressure, which acts like a vacuum that pulls the particles towards it. So for example, if you vibrate the strings of this guitar, the sound propagates through the medium through the oscillation of the air molecules, which interact with neighboring air molecules to propagate the disturbance. So you get repeated regions of compression and rarefaction, and this disturbance propagates and can be heard at some distance away. So note that the particle itself is not moving from here to the person's ear. The disturbance propagates through the medium, through the interactions between oscillating particles and their neighboring particles. So for example, if you track one particle and take the vertical axis as the displacement of the particle from equilibrium in the horizontal direction, and the horizontal axis as time, then this particle starts at the equilibrium position and oscillates back and forth in a periodic manner. So again, in this type of plot, this distance is the period of the oscillation, and in space, the distance between two compression regions is the wavelength. At a higher temperature, meaning the air particles have a higher average kinetic energy, results in a higher wave speed through the medium. In a transverse wave, such as a light wave for example, where the wavefront propagates in this direction at the speed of light, the direction of the disturbance is perpendicular to the direction that the wave propagates. So for example, if we look at a photon, it's going to oscillate back and forth in a perpendicular directions to the velocity of this wave front. So another example is this wave propagating in water. So for example, if a rock is dropped in a pond, so the wave front is propagating in this direction at some velocity. So at the crest of the wave, we have a water particle that's moved upwards, and at the trough, we have the water particle that's moved downwards. So these are examples of transverse waves. Similar to the disturbance we saw in the string. Now a sound wave is an example of a longitudinal wave. So for example, if a sound wave propagates through air, we see the wave front propagating in this direction, and the sound particles oscillate back and forth in the direction that's parallel to the velocity of the wavefront. So in other words, the direction of the disturbance is parallel to the direction of propagation of the wave. And we model sound waves as mechanical longitudinal waves. So if we look at a snapshot in time and measure the pressure at several points along this line in the medium, we see the variation of pressure with the horizontal position along the medium as periodic. So as we've seen previously, at the high pressure regions, we have compression, and the rarefaction regions are the negative pressure regions. Suppose we have a speaker, and this diaphragm moves back and forth at some amplitude and frequency to cause a sound wave to propagate through an air medium. And using an oscilloscope, we measure the pressure at some point in the medium over time. So as the disturbance propagates through this point, we have the pressure being at the atmospheric pressure, rising due to the air particles being compressed, and then it drops below atmospheric pressure, which we call rarefaction, when the air expands. So therefore the particles oscillate back and forth and interact with the neighbouring particles for the disturbance of a sound wave to propagate through this medium. So recall the sound wave is a longitudinal wave, and typically the amplitude of a wave is the maximum displacement of the wave from its equilibrium position. But in the case of a sound wave, being a longitudinal pressure wave, the amplitude can be determined by the maximum increase or decrease in pressure from the equilibrium pressure. So in this case, we see the pressure wave is periodic and the amplitude of the oscillation is measured from equilibrium to the maximum pressure or the minimum pressure. So if the diaphragm of this speaker oscillates with a higher amplitude, then an increasing amplitude increases the loudness of the sound, which is heard at another point in the medium. So loudness increases with an increase in amplitude. Now on the other hand, the pitch of the sound increases with frequency. So if the diaphragm of this speaker oscillates back and forth faster, then we get a higher pitch. So for example, and for a lower frequency, the pitch decreases, which will sound something like this. Now the energy carried by a wave increases with an increasing amplitude, and specifically is proportional to the squared amplitude. So for our wave propagating on a string, we can determine the total energy of the wave as the kinetic plus the potential energy, and you'll need calculus to derive it using the solution to the wave equation, which is beyond the scope of this course, but we'll just interpret the result for a travelling wave in a string. So we have 1/2 by the linear density multiplied by the square of the frequency of the oscillation multiplied by the squared amplitude by the wavelength. So remember that the frequency is the reciprocal of the period. So the lower the period of the oscillation, the higher the frequency, and the higher the energy carried by the wave. And similarly, a higher amplitude means that the wave carries more energy. Periodic waves have regular repetitions that can be described using a period and a frequency. So a typical example is a sound wave that's generated by the oscillation of the diaphragm of a speaker. So if we measure the pressure in this air medium at different points at a particular time t, then we see that part of the air is compressed and part of the air expands. So these are the compression and rarefaction regions. So this repeated compression and rarefaction results in the sound wave propagating from the speaker to another point in the medium without transferring any particle to that point. So this graph represents the pressure versus the distance from the speaker at a specific time t. So this is a snapshot of the medium at a particular time. So we have a compression region followed by rarefaction, back to compression, and so on along the x direction. Now on the other hand, if we monitor the pressure at a specific point in the medium, so at time t equals 0, the air is in compression, and after some time t, the air expands, and then it gets compressed, and then it expands. And this continues on as the wave propagates through this point. So using this plot over here, the period is the time taken for one oscillation of the wave to complete. So for example, if we start from this point, we have the maximum compression of the air, followed by the maximum expansion, and back to maximum compression. So that's one cycle of oscillation, being equal to the period. So note that this plot is the pressure versus time. And the frequency is the rate at which the wave repeats. So the period is the reciprocal of the frequency. And we'll look at some numbers to make sense of this. Now the amplitude is the magnitude of the maximum increase in pressure or decrease in pressure from the equilibrium pressure. So we may take our reference pressure initially as the atmospheric pressure for the air medium. And the energy of a wave increases with an increasing frequency. So we saw this from the energy equation for a traveling wave on a string. And the higher the frequency of the sound, the higher the pitch. So it'll sound something like this. Whereas a low frequency sounds something like this. Now if we use this plot instead of the pressure versus the distance from the source of the sound, the distance between successive corresponding positions, such as the peaks or troughs on a wave, is the wavelength. So for example, here we have peak to peak. So this is one way we can visualize the wavelength. Now a sinusoidal wave can be described by similar equations to a harmonic oscillator. So for example, we may measure the displacement from equilibrium or the pressure at a specific location in the medium as a function of time, and that could be represented by a sinusoidal wave. So for example, we have the pressure as a function of time is equal to the magnitude of the maximum pressure by cosine of omega t. So recall that omega for the harmonic oscillator, being the angular frequency, was equal to 2 pi by the frequency in hertz. So we can write this as A by cosine 2 pi f by time. So in our case here, the frequency is 50 hertz. So the period is equal to the reciprocal of the frequency, which is 0.02 seconds. So as we can see, this is the time to complete one cycle of the oscillation. And in this case, we took the amplitude as 1 Pascal, and the sound pressure is typically represented as a sound pressure level in decibels, and there's a formula to convert to that. But for now, this pressure is representative of a sound pressure level of 94 decibels. So here our units of pressure are in pascals, and time is in seconds. Now alternatively, the pressure as a function of x is equal to the amplitude of pressure by cosine of 2 pi on the wavelength by the distance from the sound source. So as we can see, at x equals 0, or where x is a multiple of the wavelength, we have the maximum pressure. So we have an oscillation between compression and rarefaction, according to this cosine function. So when x is equal to the wavelength, which is this distance between those compression peaks, then we get cosine of 2 pi being 1. So for the wave to travel a distance equal to its wavelength, that's equal to the wave speed by the time taken for the wave to complete one full oscillation, which is the period. And recall the period is the reciprocal of the frequency, so that gives a relationship between the wavelength and the frequency being the speed of the wave through the medium on the frequency. So in our example here, the speed of sound is 343 meters per second in an air medium with a temperature of 20 degrees. And our frequency of the oscillation is 50 Hz. So we have 343 on 50 gives a wavelength of 6.86 meters. So our pressure here is in pascals, and the distance from the sound source is in meters. And I'll write down the sound pressure level formula, which converts the sound pressure to decibels for your reference. So the sound pressure level is equal to 10 by log base 10 of the pressure on the reference pressure squared. So the reference pressure is 2 by 10 to the minus 5 pascals, which is the lowest sound pressure that can be heard. And from that, you can substitute a sound pressure and obtain a sound pressure level in decibels, which is a typical scale used to represent the loudness of the sound. A wave that travels from one medium to another can be transmitted or reflected, and this depends on the properties of the boundary separating the two media. So for example, if our medium 1 is a thinner string that has a lower mass compared to the string being medium 2. So recall that the wave speed in a string was equal to the square root of the tension force in the string on the mass per unit length of the string, being the linear density. So if m1 is smaller than m2, then the wave speed in medium 1 is going to be greater than that of medium 2. So considering this incident wave pulse propagating through string 1, then when it gets to the boundary, string 1 will exert a force on string 2, pulling it upwards. And by Newton's third law, that force is equal and opposite to the force exerted by string 2 on 1. Now because string 2 is heavier than string 1, so it has a higher inertial resistance, it's going to accelerate upwards by a small amount at the boundary compared to string 1. So consequently, the reflected wave is going to be flipped upside down when it moves back through string 1. And the transmitted wave is going to have a smaller amplitude compared to the incident wave. Now on the other hand, if string 1 is heavier than string 2, This means that the incident wave speed is lower than a transmitted wave speed. So in this case, when a wave pulse reaches the boundary, it'll exert a force on string 2. And let me move this a bit. And by Newton's third law, string 2 exerts an equal and opposite force on string 1. But because string 2 is lighter than string 1, so it has less inertial resistance, then it's going to accelerate upwards more than string 2 accelerates downwards. And consequently, the reflected wave pulse remains upward, but has a lower amplitude than the incident wave pulse when it's travelling backwards through the string. So recall the energy of a wave is proportional to the square of the amplitude. So because the transmitted wave has a higher speed, it has a higher kinetic energy, and therefore the reflected amplitude is lower than the incident amplitude. And note that the frequency of the wave does not change when it travels from one medium to another. And if you look at a simulation to make this more clear, if we have medium 1 having a lower density than medium 2, and we run a simulation, as expected, the heavier string is harder to pull upwards compared to the string with a lower density, so the reflected wave gets inverted. Now on the other hand, if we flip these scenarios, so we have a heavier string to a lighter string, and run the simulation, as expected, the reflected wave remains upright. And I'll link this simulation for you in the description so you can compare these results with the concepts that we just covered.